actually understand that complete supply chain, track all of the suppliers at all tiers, and give the supply chain operators the visibility that, oh, there's going to be a problem with this magnesium part, you better line up alternative suppliers. A lot of that goes through things like ports. So the amount of material that flows through a port like the Port of LA, Port of San Francisco, Port of Seattle, or the New York on the East Coast is huge. And all of those ports are impacted by COVID. They're all impacted by changes in what's going on in China. China is still much more on lockdown than COVID. You know, today, if you try to travel to Japan, you require a visa to get in. You have to prove that you're there on a business purpose. So we are not integrated in the same way we were pre-COVID. So the ports become often the first place you understand that you have a supply chain problem. But we can see the ships in the sea. We can see where they are docked. We can see the shipping containers on the docks and understand what's going on to make sure that we have visibility into those supply chains, even when they grow internationally. Finally, if you are, let's say you're an investor and you want to invest in let's say you want to invest in an office building in downtown Detroit, you'd like to know a lot of things before you made that investment. Are the factories back up? Are they making cars and trucks? Are they getting completely killed by Tesla and they're not making cars and trucks anymore? How many shifts are they running? What's the demand? How many people are working from home? How many people are back in the office? So if you're an investor or an insurance company or a bank, you want to understand what's going on with real property, and you want to understand what's going on in shopping centers, what's going on in office buildings. All of that we can get by appropriately analyzing the geospatial data. Now let's look at one very specific example that was quite dramatic a few months ago and still ongoing, is in an ongoing way. When the Russians invaded the Ukraine, we were able to track the refugee crisis starting out of Kharkiv, which was one of the major cities in the Ukraine that was most effective because it's in the eastern part of the country. We were literally able to watch on a day-by-day basis, an hourly basis, the number of devices through anonymized cell phone pings and through satellite imagery, the number of devices and the number of people leaving Kharkiv. And not only the fact that they were leaving, but we were able to see where they were going. We were able to track the lines of movement as people left initially right after the invasion. They were near Kharkiv, and then gradually they spread mostly into the western parts of the country. And then out of the country, we could see the border crossings. The border crossings actually lit up without even having to know where they are, looking on maps or something. The border crossings lit up in our charts. We were able to see the border crossings and then see people going to Warsaw, people going to Bucharest and other parts of Europe. Turning into refugees. And this is important not only to understand the social and environmental impacts of a crisis like this and understand where to direct aid, understand the real impact of these kind of conflicts. We can also look more directly at military questions. For instance, in the Syrian conflict, there was a point in time when the airfields that were previously civilian started to move over to being military. And our computer vision algorithms, which run all in the cloud, we're able to run at very large scale, over thousands and thousands of images, are able to actually tell the difference between civilian planes and military planes, and indeed within military planes, the difference between different kinds of military planes. We were literally able to watch the airports convert from civilian to military as we saw fewer and fewer civilian planes, fewer and fewer cars in the parking lots where the people would have parked to take flights, and more military vehicles. And looking more closely at different kinds of military vehicles, we're able to look at the concentration of different kinds of planes in different bases. Now, this is something a human could do. The problem is that there are just too many military bases and there's too much imagery. And we can take every military base, every day, every kind of plane, every kind of truck, every kind of military vehicle. And in this case, at the Quezon Air Base near Taipei, we were able to see for the first time J-20s, which is the Chinese equivalent of a stealth fighter, suddenly showing up at this base in Taipei where they had never been before. And that's the kind of pattern we're looking for to understand changes in the world and changes in the deployment of forces around the world. And you think about this running at scale, think about every military base, every factory, every farm, really starting to light that up and understand the world in ways we never had before. Indeed, the mission statement of the company of Orbital Insight is to understand what we're doing on into the Earth and make that information available to decision makers. So in this case, we counted over 53,000 aircraft using over 2,000 satellite images. This is one of the reasons, by the way, that cloud computing is so important for us. We would not be able to stand up, as a startup, we would not be able to stand up enough GPUs to suddenly process 2,000 satellite images. But since we're doing cloud computing, we can stand up as many GPUs as we want, process as many images as our customer wants to see for some particular Go project, and then turn those GPUs loose after we're done with them, and let somebody else make use of them. So think about now what this means to different kinds of decision makers. So if you're a supply chain manager, you want to know whether your supply is safe, whether or not the raw materials that you need for your factory are still available out to tier 1, tier 2, tier 3, tier 4 suppliers. We give you the ability to monitor that supply chain. If you're a consumer, or indeed if you're an environmentally responsible consumer goods company, you want to understand the true sourcing of your raw materials and the true impact of that sourcing, all the way back to which farm, which smallholder farm did this palm oil or cocoa or coffee beans come from, and is that farm engaged in deforestation? Has that farm been managed responsibly for the last decade? If you are looking at, say, a hurricane, this middle chart here is looking at the effects of a hurricane. As global events, global climate events get more and more extreme, we're able to look at the building destruction. So basically look at a before and after image, run the computer vision algorithm on the before and the after, and we can immediately tell you which buildings have been damaged in a serious way by the hurricane. So helping with climate change, helping with environment, helping with recovery from major events, helping with supply chains, helping with environmental sustainability. And then, as I mentioned before, helping with investment as well, helping understand where shipping containers are in the world, how that's changed, how the shipping lanes are moving, how much grain is still coming out of the Ukraine, and where is it being replaced from, if it's being replaced, how much oil is still being produced. Most oil is stored and floating in oil tanks, and we can actually look in satellite imagery at the height of those lids and understand, are the Saudis pumping more oil to try to make up for the shortages of Russian oil? Are the Russians still pumping oil and storing it and floating their oil tanks, or have they slowed down their pumping now that they can't sell it in Europe? All of these are really important questions for managing the world's supply of energy and other critical raw materials, especially, as I say, in the face of an increasingly chaotic world order. So what this all means is that by taking geospatial data, of which we now have an abundance, thanks to the lower and lower cost of getting satellites into Earth orbit, and the other IoT data that we have, plus the artificial intelligence to run computer vision algorithms and data science algorithms and make sense of that data, we're able to take these two together and work at scale to give insights about the world. And that is what we do at Orbital Insight. Thank you all for listening.
Please welcome the Chief Technology Officer and co-founder at Zoox, Jesse Levinson.
Hey, thanks for having me here today. Let's see if this clicker works. There it is. Excellent. Thanks for waiting. So my co-founder and I had a unique vision when we started Zoox in 2014. And our idea was to create a purpose-built, fully autonomous vehicle designed for riders instead of drivers, and to deploy them in fleets so that we could sell rides instead of selling entire cars. At the time, many people thought we were nuts, and they might have had a point, but when we looked at the current state of transportation, we wondered why everyone accepted that things had to be this way. So most horrifying is that globally, car crashes kill well over 1 million people a year, and that's actually more than, well, almost 4,000 people every single day, which is several times worse than COVID these days. It also turns out that we only use our cars about 4% of the time, which means that they're just sitting idle and depreciating the other 96% of the time. So they're incredibly wasteful, economically, but also environmentally, because not only does driving a car create pollution, but building a car is not so great either. There's a lot of stuff in cars, as it turns out. Next, 1/3 of city traffic is caused by people searching for parking, which doesn't just suck for the people looking for parking, it makes congestion worse for everyone else too. Now, back to pollution. A quarter of the air pollution in the US is caused by transportation. And finally, we collectively spend 400 billion hours driving each year. So even conservatively, that's trillions of dollars of wasted time every year. So hopefully it's pretty clear that making and selling lots of cars isn't great. And while electrifying them is mostly a good thing, that only makes the situation marginally better. We're going a lot further than that. What makes Zoox unique is that we've been working on a ground-up, purpose-built design from the first day we started the company, almost 8 years ago. Now, we're finally starting to see some of our competitors acknowledge that purpose-built hardware is the optimal solution, but most players in this space are still focused on retrofitting conventional vehicles with sensors and other advanced hardware. And even the supposedly ground-up robotaxis that other companies have pre-announced are actually built on top of conventional car chassis. So they're missing a lot of the unique advantages we built into Zoox, like bidirectionality, four-wheel steering, and a ton of safety and redundancy features. So our view is that the full realization of autonomous mobility requires a vehicle that is purpose-built for AI to drive and humans to enjoy. And that's exactly what we're building. A lot of the work is creating the AI software and making sure it's safe enough. But the best way to ensure it's possible is to give ourselves major advantages in the hardware, like sensor pods on the top 4 corners of the vehicle that can see absolutely everything. Here's a slide that our CEO, Aisha Evans, shared at Remars back in 2019. It's actually from our original pitch deck when we founded Zoox in 2014. And we think it's a great visual summary of how we look at the opportunity. We didn't think this was an exaggeration then, and we're even more sure it's spot on now. So today, I'm excited to share more about how our vehicle works and some of the progress we've made in the last few years. Here's what a Zoox looks like in its natural habitat. We revealed the world's first purpose-built operational robotaxi in December 2020. It's capable of driving up to 75 miles per hour in both directions. And we didn't just show a prototype, we actually showed it driving. This is us driving in downtown San Francisco, but we did have to close the roads off to the public and only interact with Zoox agents. And the reason was that even though we had almost all of the functionality we needed to drive autonomously, we were still progressing against our safety case, which is how we can quantitatively demonstrate our safety even amongst the chaos and uncertainty of the real world. Since that time, we've advanced our urban driving capabilities, taking the learnings to our ground-up vehicle to validate our safety case so that we can prove we drive significantly safer than a human driver. One of the most important developments in the last few years is that when we test our L3 vehicles in dense cities like San Francisco, Seattle, and right here in Las Vegas, they now make significantly fewer mistakes than even attentive human drivers, and that's a big deal. It doesn't mean that we handle every single possible scenario better yet, and we are still working on some of the toughest corner cases, but it's an important metric, and it's great progress. These videos show some of the complicated scenes we handle autonomously day in and day out, and it's particularly cool to see the full 3D sensor fusion output while we drive. As far as I know, we're still the only company that releases this level of perception output, and we've been doing it for a few years now if you want to check out our YouTube channel. Let's talk more about the technical challenge of teaching a robot to drive. Before the vehicle can plan its trajectory, it needs to know what's going on around it, which is called perception, and then what other agents are likely to do, which is called prediction. As I've mentioned, we want to give ourselves the best possible chance of knowing exactly what's happening. Early attempts at autonomous vehicles focused on retrofitting conventional cars with sensor suites as a way to fast-track their way to commercialization. And while it's definitely possible to get a reasonable degree of functionality with something like the car on the left, we actually are much more into what's on the right. We are very confident that the optimal approach requires what's on the right. Besides the suboptimal customer experience, especially if there's a creepy, disembodied steering wheel kind of just moving by itself, the actual shape of a car just isn't optimized for AI vision. You can see that there's a hood sticking out in the front. And while it's possible to add even more sensors to the hood, which gives you some visibility when there's unprotected cross traffic, at best they're at waist level, which means they definitely don't have the best possible view of the world. So we've optimized perception by designing a vehicle with the ideal sensor placement and maximum redundancy. Our vehicle is symmetrical, with each top corner featuring a custom sensor pod, which gives us 270 degrees field of view on each corner. And the really cool thing about this architecture is that if you can see at least one corner of the vehicle, you know that it can see you. Now we're going to have a pop quiz at the end of the talk to make sure you've all memorized the